Okay, so neither the Raspberry Pi Foundation nor Raspberry Pi Limited, the commercial company that spun off from the Educational Foundation, is responsible and now responsible for making the hardware, writing the software, and that's the folks I work for, sends things into space. Sending things into space really isn't what we do. But that hasn't stopped our products from acquiring flight heritage, because other people have an alarming tendency to send them into space on our behalf. Some of them are sitting in this room. Don't think I don't know who you are. I will be talking to you in corners later. There is one exception to this general rule, which as satellite folks you might not know about. In collaboration with 𝗖cie, two space-hardened Raspberry Pis equipped with environmental sensors and camera modules for Earth observation were sent to the ISS back in 2015. These computers were used by school kids to run experiments with crew assistance on board the station for 7 years before being downmasked just last year. They ran without fault the entire period on orbit. More recently, two upgraded Astro Pis, this time built around the Raspberry Pi 4, equipped with an enhanced set of sensors, our nearest camera module, and a Google Coral TPU, were launched and have been on station now since 2021. They actually went online last year now, so they've been working for about a year. But our own Astro Pi units aren't the only Raspberry Pis on board the station. One of our problems, and this is why I'm here, is that when people send Raspberry Pis into space, they forget to tell us about it. And sometimes we only found out months, even years later. We would love to give you folks publicity. We would love to write about you. We would love to film video. Please tell us when you put something on a satellite. Anecdotally, at least, I do know that quite a few experiments running on board the ISS are built around Raspberry Pi hardware. The 𝗖cie cryptographic ice cube experiment, for instance, is built around a Raspberry Pi Zero. The experiment's attempting to overcome the problems with radiation hits when sending encrypting communications in space. It uses a Pi Zero more or less off the shelf, the only difference that the board had to be covered with conformal coating to fulfill the standard safety obligations for operating on station. But they aren't just used in shirt sleeve environments on the station. The Raspberry Pi Zero went on board the 𝗖cie satellite technology .1 satellite as a secondary payload. And we're seeing that quite a bit. A lot of Raspberry Pi Zeros with camera modules are ending up in secondary payloads in larger satellites, in more or less off-the-shelf configurations. The only satellite we actually know about, for a fact, that was entirely Raspberry Pi based was GasPax. So if anyone did actually have something in orbit that was entirely Raspberry Pi based, come and tell me. GasPax was a CubeSat, a getaway special 1U CubeSat built by the students at Utah State University. It operated for 117 days from deployment in January last year when it got kicked out of the ISS until re-entry later in the year. It was intended as a technology demonstrator mission just to test the deployment of a 1 meter long inflatable boom for passive altitude stabilization. The Pi Zero, again, was used as a satellite's flight computer, and Raspberry Pi camera modules were used to take pictures of the boom deployment. So what I was intending to talk about today is testing. Right now we have vacuum testing ongoing at Boeing and radiation testing ongoing at NASA JPL. But what I don't have to give you is any of results from that. The results are still held up by NDAs and lawyers, so I can't share any details about that. We're hoping to publish them, well, publicly, sometime in the new year. And in the meantime, come talk to me in the pub, maybe? So instead, what I'm going to talk about is, well, the things that we make. And as I said, the Pi Zero is probably the board that's acquired our most flight heritage. It's a relatively tiny 65mm by 30mm form factor Pi, and so Pi Zero was the original one, and then its successor Pi 2. They're built around the Broadcom BCM2385 and BCM2387 silicon. Although in the Pi Zero 2's case, we wrapped it inside our own SIP package, the RP3A0. Both of these chips are based on a relatively older 40nm process and are therefore somewhat less vulnerable to radiation events than hardware built around newer processes. They're commonly flown, as I mentioned, alongside our camera modules. We have quite a range of these now, so hopefully you can find one that works for you. The original 5 megapixel camera was released back in 2013. It was followed by an 8 megapixel camera module 2 a couple of years later. Weirdly, the first camera module is pretty much the only product we've ever discontinued. Like everything else you can still buy. You can still buy an original Pi if you want one. I'm not sure why you'd want one, but you can still buy one if you want one. The latest model is a 12 megapixel camera module 2. It was released earlier this year. And all these cameras come in visible light and infrared versions, while camera module 2 also comes in a standard and wide field of view mode for a total of 4 different variants. Additionally, there's a 12 megapixel, what we call high quality camera, which comes with a CS or M12 mount variants for external lenses, and there's a global shutter camera, which was released not that long ago. There's no infrared versions of the HQ or GS cameras, but the IR filters can be removed if needed. But I guess the thing I really want to talk about today is our own silicon, the RP2040. The RP2040 microcontroller was developed in-house by our own ASIC team at Raspberry Pi in Cambridge, just down the road from ARM. It's a dual-core Cortex M0 Plus running at 133 megahertz. It's also built on a 40-nanometer process. And it's our idea of a perfect mid-range microcontroller based on years of using other vendors' devices and our own projects and products. Firstly, it has 2 fast symmetrical cores. So a pair of ARM Cortex M0 Plus cores, clocked to 133 megahertz. So decent integer performance. You can use one core to run applications and the other to supervise hardware, or run application code on both cores with FreeRTOS or MicroPython, or directly in C, or even bare metal ARM assembler. It has plenty of RAM. Unlike a lot of microcontrollers in this class, it has 264 kilobytes of RAM, so you can concentrate on implementing features rather than optimizing your application size to fit in 4 kilobytes of RAM. Its fully connected switch connects to the ARM cores and DMA engines to 6 independent RAM banks, allowing to squeeze every last drop of performance out of that system. Additionally, and this is a design choice that's been somewhat controversial, there's support for 16 megabytes of off-chip flash via a dedicated QSPI bus. And that means you can tailor the amount of flash RAM you put on your board to your actual requirements. It also, considering the supply chain crisis of the last few years, means you can pick and choose between flash chips you can actually buy, which has become less of a problem in the last 6 months or so, at least, thank heavens. Thirdly, it was designed for flexible input-output. It has 30 general-purpose GPIO pins, and we provide all the usual interfaces: 2 hardware UARTs, SPI, I2C, 16 PWM channels, along with USB 1.1 support, and a 4-channel ADC. But RP2040's unique feature is something called programmable I/O, PIO. It's the PIO subsystem that makes RP2040 unique amongst microcontrollers, at least. It enables software implementations of protocols such as SDIO, DPI, I2S, and even DVI-D, HDMI, without having to resort to bit banging the implementation, and without affecting or even using the 2 main cores on the chip. It's programmable in the same sense a processor is programmable. There's 2 PIO blocks with 4 state machines that can independently execute sequential programs and manipulate GPIO and transfer data. But unlike general-purpose processors, PIO state machines are highly specialized for input-output and focus on determinism, precise timing, and a close integration with the fixed-function hardware. And all 8 state machines have independent, simultaneous access to all of those GPIO pins. Beyond this, the chip has a fully connected switch at the heart of the bus fabric. You can arrange for the cores and DMA engines to run in parallel without contention. And finally, as Cortex M0 Plus lacks a floating point unit, we commissioned Mark Owen, the author of QFP-lib libraries, which are substantially faster than the equivalent GCC libraries, to have floating point on chip. And you can transparently use that with our CSDK, which I'll talk about in a little bit, and it's licensed for use with any RP2040-based product. So you can do relatively faster floating point despite the fact that this is a Cortex-M0+. Which brings us to Raspberry Pi Pico. This was our first microcontroller class product and has been built around the RP2040. It serves both as a demonstration board and a development platform who want to develop their own products or platforms with 2040. If you look in the conference bags you'll find one of these boards in a small box. Scanning the QR code should take you to our pages supporting, well, space folks. And even if you don't put it into space, I hope you have fun with it. And if you do send it into space, send me an email. You'll find more information about the new microcontroller board at this URL. Along with documentation, you'll also find schematics and layout files and BOMs, both for Pico itself, which is entirely open source. It's released into the design's released into the public domain, but also for something we call a minimal viable board. This board consists very nearly of the minimum amount of circuitry you're required to make a functional design around RP2040 that can run your code. The PCB only has 2 copper layers, it has components on top and one side only. It's a relatively large minimum track width. Clearances and hole size should make the design really easy to cheaply manufacture from your PCB supplier of choice. The minimal viable board and the choices we made in the design around it are discussed in this book, which is Hardware Design with RP2040. It's actually a really quite interesting thing. You'll see a lot of this for software, but it's sort of unique in sort of the microcontroller world that I've seen, which is actually discusses why you make various choices, like why you put these passives in various places in the board with respect to the microcontroller. So it's a really good place to start if you want to build something around the chip. One of the advantages of using our hardware, it means that you can just, during your design phase, you can build using something like a Pico and then move to industrialized versions of the hardware when you're flight ready, which brings us to the debug probe. This is an all-in-one USB to debug kit that provisions all necessary hardware and cables for solderless plug-and-play debugging with Pico. Features a processor serial debug interface. By default, it's ARM serial single-wire debug, but other interfaces can be supported, and a standard UART. And of course, our debug probe is built around 2040. In fact, if you have 2 Picos, you can just take the code that runs on this board, run it on one of the Picos, and debug one Pico with another. So that's quite fun. So we've really tried to make it as easy as possible to reduce the barrier to entry for folks when you're getting started with microcontrollers for the first time, as I know some people are. There's official CSDK for Raspberry Pi Pico, a GCC-based toolchain with a Visual Studio Code integration, along with other platforms like 𝗖𝗁 and Eclipse, if that's your IDE of choice. But this supports all RP2040-based boards, and if you want your hardware explicitly supported inside the SDK for other people to use, just make a pull request against the SDK's GitHub, and you can get a board definition file put in the standard SDK distribution. However, for folks that prefer higher level languages, Damien George, creator of MicroPython, there's a polished port of RP2040 to MicroPython. And it exports all of the chip's hardware features, including PIO. So you can actually include PIO assembler code in your MicroPython. For those of us that remember 8-bit computers like the BBC Model B, this is pretty much equivalent to sticking peek and poke commands and assembler code directly in your BBC Basic. I see a couple of smiles out there. People do remember that. Okay, that's nice. I'm not as old as I think. But we aren't alone in providing hardware support for 2040. There's other options. There's a CircuitPython port, which is the other Python port to ARM. There's 2 Arduino core ports. One's a community port, which sits directly on top of our own SDK. And then there's the the Arduino official port, which sits on top of ARM's embed platform. There's swings and balances and choices to be made between the two of those if you're Arduino people. There's also a FreeRTOS implementation for RP2040. Again, there's 2 ports here. One's a single core and one's an SMP core. I think we're actually the first SMP platform that FreeRTOS supported. So, sorry for how brief this was. I more or less had to write this last night as the lawyers finally told me I couldn't talk about testing, which is what I wanted to talk about. And I'm going to be around for the rest of the conference, so feel free to corner me. I'll be happy to tell you the good news about Raspberry Pi. Thank you.